In today's video, we will use biolayer interferometry, otherwise known as BLI, to perform a kinetics interaction study between Herceptin monoclonal antibody and a recombinant FcRn protein. Protocol information is available at www.agrobiosystems.com. You can request the protocol for this product by sending an email to techsupport@agrobiosystems.com. Before starting, please bring all reagents and samples to room temperature before use. The first step is to do protein reconstitution. Please reconstitute the protein following the COA. In this video, reconstitute with 250 microliters ultra-pure water to prepare a 100 microgram per ml of biotinylated human FcRn heterodimer protein. Dissolve at room temperature for at least 30 minutes, gently mix to ensure complete dissolution, then the standard curve can be ready to be generated. During this time, prepare a 1x PBS buffer with pH of 6.0. Taking some ultra-pure water from the water purifier into the centrifuge tube, measure 45 milliliters with a graduated cylinder. Pour 5 milliliters of 10x PBS buffer into the same cylinder. Now we have 50 milliliters of the 1x PBS buffer. Afterwards, transfer all 50 milliliters of the 1x PBS buffer to a new centrifuge tube to adjust the pH. Add about 10 microliters of 0.25 normal phosphoric acid into the tube. The final pH of this reagent is 6.0. When pre-wetting the biosensors, you'll need to put the biosensor into a buffer to remove the protective agent from the biosensors. Add 200 microliters per well of 1x PBS buffer on the F-bottom black microplate from Grinner using strip 1. Place the plate under the biosensor tray and pre-wet the SA biosensors from Forte Bio one by one. Incubate for 10 minutes. Next, based on our manual, prepare serially diluted Herceptin samples and 2 microgram per milliliter of biotinylated human FcRn protein. Add 1,470 of 1x PBS buffer into the first tube. Following, add 728 microliters of 1x PBS buffer into the second tube, and then add 250 microliters of 1x PBS buffer into the third through seventh tube. Following, add 30 microliters of biotinylated FcRn recombinant protein into the first tube to get the 2 microgram per milliliter biotinylated FcRn protein. For serially diluted Herceptin samples, aspirate 5 microliters of Herceptin from Roche into tube number 2 to make 1000 nanomolar of Herceptin. Remember to gently vortex briefly by using pipette to ensure that each tube is well mixed. Next, take 250 microliters of the 1000 nanomolar Herceptin from tube number 2 into the third tube. Then complete the serial dilution for tubes 3 through 7. And the molar concentration of Herceptin in the last tube will be 31.25 nanomolar. Now it's time to set up your plate. In this video, add 200 microliters per well of 1x PBS buffer into the first column of the black microplate as baseline number 1. Then add 200 microliters per well of 1x PBS buffer into the column number 3 of the black microplate as well. This is baseline number 2. Meanwhile, the wells in strip 2 row H and strip 4 row G are to be filled with 1x PBS buffer as reference wells. Next, load 200 microliter per well of 2 microgram per milliliter of biotinylated human FcRn protein as ligand to the wells from row A to row G in column number 2 of the black microplate. Afterwards, add 200 microliters per well of the serially diluted Herceptin in column number 4 of the black microplate. 1000 nanomolar in row A and H, row B to row F sequentially from 500 nanomolar to 31.25 nanomolar. Finally, place the 96 well black plate as well as the sensor rack into the corresponding compartment of the Octet Red 96E machine. Click on this instrument to start initializing. Choose the second option, then click on the green arrow. On the left side is a 96 well plate design. In the first column, put 1x PBS buffer. I choose Set Well Data first. Name the sample ID as PBS. Then right-click, showing this column as a buffer. In the second column, put 2 microgram per milliliter of biotinylated human FcRn protein, showing as a ligand. The last well we filled with 1x PBS buffer, I also put this well as a buffer. In the third column, put 1x PBS buffer, showing this column as a buffer as well. In the fourth column, put serially diluted Herceptin monoclonal antibodies, except the penultimate wells, which we filled with 1x PBS buffer, so put this well as a buffer too. After that, change the sample ID accordingly. It will be convenient for us to record. For A3 through H3, the sample ID is PBS buffer. For A2 through H2, the sample ID is the lot number of the biotinylated human FcRn protein. Concentration is 2 microgram per milliliter. From A4 through H4, the sample ID is Herceptin. Molecular weight is 150 kilodaltons. Change the starting value to 150 micrograms per milliliter. We can see its corresponding molar concentration showing up on the table. For H4, please remember to change to the highest level dose. We have one more step. We call it the assay definition. Some of the steps, such as association, dissociation, baseline, and loading, need to add. All steps, shaking speed should be set to 1000 RPM. Other steps set the time to 60 seconds. For the loading step, time set is 600 seconds. Set the threshold to 3 nanometers, and make sure the step is terminated when the threshold is achieved on any one channel. Now we have to tell the instrument what the first step is. The first step is the baseline. The second step is the loading. Then the third step is baseline once again. The next step is association, and the last step is dissociation. I put the sensors at the first column in the sensor compartment. The next step is to review the experiment. So run the experiment where exactly you want to store the data, and give this experiment a name. As sensors are not pre-wet, we can tell the software to delay for 600 seconds. Set sample plate temperature at 30 degrees. Now go for the experiment. The first step is baseline. The second step is called loading. Then the third step is baseline 2. Weakly bound substances get washed off here. Next step is the association step. This is where the Herceptin monoclonal antibodies will bind to the ligand. And the last step is dissociation. The biosensor is moved back to the wells which contains a buffer. Analyte will dissociate from the ligand and we can generate the dissociation curve. Now, since acquisition is done, it's time to go for the data analysis. There's a folder here, double click on this. A new page will open. Go to processing here. In the processing tab, you will see the raw data, subtracting one of the columns with 0 concentration. Then align y-axis to make the baseline. Set up time range from 55 seconds to 59 seconds. Now go for the process data. In the analysis part, we have 6 data points. To calculate the rate constants, always choose the association and dissociation. For binding models, please choose 1-to-1 binding. In terms of what kind of fitting, most of the times when performing interactional studies, always go for the global fitting. Global fitting will respect the color and the Rmax unlinked by a sensor to perform. For the dissociation time, change to 0 to 5 seconds. Because for FcRn protein, it is fast binding and fast dissociation. This is steady state fitting. The general dissociation time is 5 seconds. Then, select all samples to change to one color. Here we change to blue. Now, try to use the entire step systems to fit the curve. For loading samples, we need to see their KD value, as well as the R-squared value. Deselect grid lines to make the picture look more concise and clear. The KD value is about 2.3 nanomolar. For kinetics evaluations, a good fit starts around 0.95. Our R-squared value is 0.9916, indicating the curve is a good fit. Finally, click Options. Select Steady State Analysis, available as a function of protein construct concentration.